Let's do some calculus. Today we're going to do related rates, and tomorrow and probably some other times because yeah, this topic is a lot, but you can do this, and I want to remind you, you can do this. So this is a really tough one. It's kind of like an intense movie where if you pay attention to something else at the same time, it's going to be pretty difficult. So give this as much of your attention as you can, and then stop when you can feel yourself like kind of just going, yeah, I'm kind of following along a little bit. Stop the video or just ask me a question at that time. Okay, so in here, this says implicitly differentiate. So that's exciting. And this says with respect to time. So far, everything that we've done has been with respect to x. So we've had the change in y over the change in x with everything so far, or dx, that why we didn't have to write this. This is going to be with respect to time. So whenever we do this derivative of anything, it's going to be dt. And how this works is we're going to be talking about the rate that different things are changing. So like there are some real world scenarios, and some are not so much, but we could be talking about like a balloon blowing up, for instance, and what is the rate that the radius is changing. That isn't going to be changing with respect to x on some axis somewhere. What it's going to be changing to is with respect to time. So as time increases and you're blowing up a balloon, what's the rate that the radius is changing? And there are other examples like this, and we're going to go through, but this is all going to be with respect to time. So if I go through this and I say, okay, well, what is this with respect to time? You can even just be thinking about it as a variable for right now. Area of a sphere, so surface area of a sphere, the outside of a sphere being like a ball, is a is equal to 4 pi r squared. And so in this, I'm going to say the derivative of a is dA dt. So dA dt, just somewhere, this is the rate area is changing with respect to time. So that's dA dt. You don't have to write this every time, but I'm just kind of saying it says state which rate is and the differential equation, what's it represent. So that's what the rate the area is with changing with respect to time. That's all dA dt. Because remember, the derivative of a variable will be 1 and then with respect to whatever this variable is, in this case t. Over here, 4 times pi is just a coefficient. So pi is not a variable. So I'm going to take my exponent of 2 times 4 pi, and I would get 8 pi r to the first power. But because this is with respect to time, I need to say times dr dt. And dr dt just means the rate the radius is changing. What is that the word? Is changing with respect to time. Okay, let's do another one. So if I've got volume of a sphere is 4/3 pi r cubed, so this is volume, the stuff inside of a sphere, and I take the derivative of v, it'd be 1, but then because this is implicitly differentiated, I would have to say dv dt. 4/3 pi is just a coefficient again, so 3 times 4/3 would be 4 pi, still I just keep it along for the ride, r squared, times dr dt. This volume, the dv dt, this is the rate. Volume is changing with respect to time. And I'm actually going to stop writing this now because this dr dt is going to be the rate at which the radius is changing with respect to time. All of these are going to be the rates that whatever that first thing is changing with respect to time. So I can say that about every single one of these. Okay, so if I do the next one, ooh, this one's a little bit crazy, but this says where c is a constant. This is really, really important. So we're treating this just as we would a coefficient in some way, or in this case, just a constant. So think about c being a number. So I'm going to first rewrite this. And then I'm going to go over here and I'm going to say, okay, the derivative of a would be dA dt, which, by the way, this would be the rate at which a is changing, or side a, with respect to time, is equal to, instead of, I forgot this a second ago, this would be to the 1/2 power. 1/2, leave the inside alone. My new exponent is -1/2. So leaving the inside alone, times the derivative of the inside. This is where it's really important that you pay attention to details, that c is a constant. Because if I do times the derivative of the inside, the derivative of any constant, think about the slope of any horizontal line, is just 0. And it doesn't matter that it's squared. Minus the derivative of b squared would be 2b to the 1st power times dB dt. And then I'm going to go one step further and just simplify this a little bit. So dA dt is equal to, this is going to be 2. This would be c squared minus b squared to the -1/2 power. So this goes down to the denominator as +1/2, or I can write it as square root of c squared minus b squared. Over here, this -2b is in the numerator. I'm just going to keep the dB dt. Looks crazy, but this is the derivative. You're going to have so many friends after this lesson. Eek. Okay, this one, r is a constant. That's so nice. You can see where this is a really big deal. Because now if r is a constant, that means this entire thing is just a coefficient. Which means the derivative of v is dv dt. Coefficients we just take along for the ride. We don't have to do the product rule on this one because r is a constant. And by the way, why r is a constant? If you think about the volume of a cylinder, like a cylinder filling up like a soup can, you're filling it up, the radius stays the same the entire time, which is why we treat it as a constant. The radius is not changing. So if we did the product rule and we did something with dr dt, that would be 0, and you get rid of that part of the product rule anyway. Okay, so dv dt, the derivative then of, let's say, I don't know, if this was volume is equal to 3h, I would have dv dt is equal to 3 dH dt. Same idea over here, because pi r squared would be acting like the 3. So I'm going to just say pi r squared. It's just a number. And then the derivative of h is 1 dH dt. So it looks similar even though pi r squared, it's weird, but it's a number. Okay, getting rid of that business just so you don't think that it's related to this problem. Okay, this is probably one of the most commonly missed because it looks scary. It's not actually scary. It's one of those, it's going to make you a lot of friends if you can write this correctly. The derivative of cosine is negative sine, but what's tricky about this is theta, or we could say x, is a variable. It is an actual function. So we have to say negative sine, sorry, I'm not even making these noises, wow, I leave the inside alone, this is the chain rule, times the derivative of the inside. The derivative of theta is d theta dt. So stick with that for a second, make sure you got it. Over here, some people are going to be tempted to do the quotient rule right away. Don't let that be you. You can rewrite cosine of theta is equal to 1/15 x. And by the way, you can see this ratio set up. Cosine is adjacent over hypotenuse. That's where this is coming from, this whole equation. On this side, though, I'm going to say, well, the coefficient would be 1/15. And then the derivative of x is dx dt. Okay, in the next one, volume of cone. A cone, if I'm filling that up, let's say with water, or think about an ice cream cone, so it's like what we think of as a traditional cone upside down, I'm filling it with ice cream, maybe melted ice cream, so it fills in all the cracks. The radius would be changing the entire time because it's small at the bottom and it's bigger at the top. The height would be changing of the ice cream, like that would be changing. So you would have to count both r and h as a variable. So to do this one, you'd have to say dv dt. And then I'm going to use this as my first term, this is the second. What's the product rule? First times the derivative of the second would be 1 dH dt plus the second times the derivative of the first. Okay, 1/3 pi is still just a coefficient. So I'm going to take 2 times 1/3 pi, so I get 2/3 pi r to the first times dr dt, because wow. Okay, this was all a lot. Make sure that you're stopping and asking questions whenever you have them. But let's do some more. Okay, now we're going to get into it. The first couple on here, and really everything that we're going to do today, is going to have you like taking steps, like breaking apart this problem, and I'm going to help you do that. And then soon we're going to not have you breaking it apart and just kind of doing all these things at once. But I just want you to kind of get an idea of these are the steps. There's the similar steps every time that you can go through. Okay, so in this problem, ooh, that's not good. In this problem, we're talking about air is leaking out of a balloon. This leaking is actually pretty important. Out of an inflating balloon in the shape of a sphere. So think about, this is a balloon, like one of those bouncy ones that you go boom, 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 and they make a noise. This is like an actual sphere. And it's saying at a rate of 230 pi cubic centimeters. Okay, that seems important. Per minute. Okay, at the instant when the radius is 4 centimeters. So there's a moment. Sounds like an instantaneous rate of change to me. What is the rate of changing in the radius of the balloon? Okay, so there's a lot to unpack here. So let's talk about that. Identify all the variables used in this problem. Well, here, if it's talking about an inflated balloon in the shape of a sphere, and we're talking about cubic centimeters per minute, it says something about volume in some way, because this is the rate that a volume is changing. That's the cubic centimeters. And I can also see that the radius is here. So volume, and there is a radius in this problem too. Identify which, if any, of the variables in the problem remain constant. I can speak. In this one, volume doesn't remain constant because air is leaking out of a balloon. If you're talking about a sphere, the radius will be shrinking. So there's none in this problem. The rates that are given or that we wish to find. 230 pi cubic centimeters per minute. This is a rate. And if we're talking about like what rate is that, the only thing out of volume and radius that would be in cubic centimeters would be volume. So dV dt, this is the rate which volume is changing. And I'm not going to write this on all of them. With respect to time. And we know dV dt is 230 pi cubic centimeters per minute. Or do we? It says it's leaking out though, which means my volume is changing and the function is decreasing, so this would be negative. And you can say cubic centimeters, centimeters cubed per minute. And the other thing I need to know is the dr dt. And how I know that is because at the instant when the radius is 4 centimeters, so there's a moment that it's like that, not constant, what is the rate of change of the radius of the balloon? That's where this is the dr dt. Later, you won't be writing it down here. You'll be just saying, oh, dr dt. This is dV dt, like kind of writing it in your problem. So I'm going to start doing that a little bit. In here, write an equation, often in geometric formula, that relates these variables in some way. The good news is on the AP test and non-test that I give you or in AP Classroom, they're going to give you anything that's more complicated than like the surface area of let's say, a cube or a box. You need to know what is the area of a circle, circumference of a circle. Some of those more basic geometric formulas, you do not need to know what is the volume of a sphere. So it would give you something about the volume of a sphere. We can see on this last page was 4/3 pi r cubed. So volume is equal to 4/3 pi r cubed. And we actually already did differentiate this on the last page, but let's just do this together. Implicitly differentiate both sides. It also says in this one, if you have anything that's constant to substitute in, but remember we said we didn't. So I'm going to just take this and I'm just going to go with it for right now and say, okay, well, dV dt, if I take, that's the derivative of this side, over here, 3 times 4/3 is 4 pi r, reducing this by 1. So I get r squared Wow, dr dt. And then there's nothing else I can do with this, except when I go down here, substitute all the instantaneous rate of change. So I'm going to say dv dt, we already know was negative 230 pi. This is where you could keep in the units, but I'm actually not going to because it gets really cumbersome on some of the bigger problems. So I'm going to just think through the units at the end. But I'm going to say negative 230 pi is equal to 4 pi. At the very end of the problem, this is where you substitute anything that happens at a moment, at an instant, because this is the derivative, the instantaneous rate of change. And I know at an instant, the radius is 4 centimeters. And then suddenly this problem gets easy peasy lemon squeezy, because it's just like any other problem you've ever done. I mean, maybe not exactly like any problem you've ever done, but on this side, I'm going to say 4 squared is 16 times 4, I think that's 64, right? Pi. And then on both sides, I'm going to divide by 64 pi. That's nice. The pi's go away. It's like Thanksgiving. The pi's go away. And negative 230 over pi is, you could keep it as negative 230 over 64, or you can say, kind of cheating a little bit and going back to what I know already. I know this, but I'm going to put the rate at which it's changing and make sure that it actually puts the units on here. So if I'm thinking about what are the units in this problem, dr dt, so I'm thinking what's happening in the numerator, what's happening in the denominator. I don't have a lot of room right now, but that's okay. The radius is changing. Radius was given in centimeters. Time was given in centimeters per minute. So here I'm going to say per minute or centimeters cubed. So I know that the rate at 4 minutes, right? So, or I'm sorry, the question said when radius equals 4 centimeters, the radius, so I'm looking up to the original problem, so right up here, that's where I was getting this from. The radius is changing at a rate of negative 3.594 centimeters per minute. We did it! So we can say at a particular moment, so when the radius is 4 centimeters, the radius is changing at a rate of negative 3.594 centimeters per minute. I'm being very intentional in the way that I'm talking about this. I'm not going to say decreasing because I can't say decreasing at a negative rate because that would actually mean increasing. So be careful with your language. If you use decreasing, the radius is decreasing, make sure that you change this final answer to positive. Okay, we did one. Let's do another. Oh, a stone is dropped into a calm body of water. So think about a stone dropping into a water, like let's say like a lake, and then you get bigger and bigger and bigger concentric circles, like one circle inside of another one. And then it says the radius of the outer ripple, so think about it getting bigger and bigger and bigger, is increasing at a rate of 1 foot per second. So far I'm seeing radius is in here in some way. When the radius is 4 feet, what is the rate of the total area? And we're just talking about a circle. So total area. Think about this as anything constant in this problem. You've got a radius and an area, and they're both getting bigger and bigger. Yes, if I do it this way. Bigger and bigger and bigger. So in this one, there is nothing remaining constant. The rates that are given, I see a radius is 4 feet, but again, that will only be for a moment, an instantaneous rate of change. So I can't put, or an instant radius in this case, not even a rate of change. So I can't put in the 4 feet yet. But this one says, oh, I know this, 1 foot per second. The radius is changing at a rate of 1 foot per second, so dr dt. So I'm going to say dr dt is 1 foot per second. And it says, what is the rate of the total area? dA dt is what I want to find. Write an equation that relates one of them, area and radius. So this is where it actually is really important that you remember the area of a circle It is not 2 pi r. What is it? Area is always in square units. This is the one, the pi r squared. This is important that you actually memorize this one if you don't have it in your head already. Area is pi r squared. I'm going to differentiate that. So I'm going to take the derivative of both sides. And I would get 2 pi r dr dt. Because, wow, don't forget. And then I'm going to substitute all the things that I know. So anything instant, I can substitute that now. dA dt is the thing that I actually want to find out. So I'm going to say dA dt equals 2 pi. The radius at one moment, the radius is 4 feet. So this is like what's happening at this instant. dr dt, we already said was from the problem, was 1 foot per second. So I would get 2 times 4 is 8 pi. And you could change this and do, I don't know what it would be, like 24 point something. But I'm just going to keep this as 8 pi. But what's really important is make sure that you have correct units. So if you wanted to think through this and you're like, well, radius times dr dt, and this was foot per second, and this one would be just a foot. Foot per second times foot would be feet squared, square foot per second. You could do that. Or you can say, well, area is how many square feet, square units are inside of something. And then time was given in seconds. So I know when the radius is 4 feet, I'm taking this right from the end of the problem. The total area, sorry, my hand's in there, is changing at a rate of 8 pi feet squared per second. Most of these questions will have something at the very end of it that will be like kind of a wrap up to everything else you've done in the whole problem. Okay, want to do another? Yeah, you do. We might even do 2 more. We'll see how long the next one takes. Maybe just 1. I feel like, I don't know. We'll see. Okay, water is leaking out of a cylindrical tank. So nice. So we're talking about a cylinder of some sort. And it's leaking. Oh no. So I'm going to stop right there and think, okay, leaking out 3 cubic feet per second. What is measured in cubic feet? What measurement? Volume is measured in cubic feet. That means dV dt is leaking, so that's the -3 cubic feet, so feet, exponent of 3 per second. If the radius of the tank, oh, there's another variable, is 4 feet, what is, ooh, it's always 4 feet? Hold on. Well, radius is here, that's fine, I can leave that here. But the radius is 4 feet, and it says it's always 4 feet. If I'm thinking about this, oh man, this picture's so good. And I've got water leaking out of a tank. Look how realistic that is. No, there's not water on my page. That's me. That's just me drawing it, everybody. It's okay. There's not actually water on my page. Okay, so it's leaking out. This radius, whether it's up here or it goes down and down and down and down, I guess I should get out of the way, down and down and down, this radius in this cylindrical tank will stay exactly the same. So the radius is constant, 4 feet. We can put it in immediately, and I will in a second. And it says, what is the rate of the depth of the water? Depth is often called height in a problem. So I'm going to say height. Oh man, that's another variable. But we've got 1 remaining constant. That's okay. And it says, what is the rate that the depth of the height is changing? So this is going to be dH dt. I said that weird. I said the depth of the height. Depth of the water, also known as height. So this is where the dH dt is what I want to find. Okay, so if I want to put this together, this is another one that I wouldn't expect you to know, but will be given to you, that the volume of a cylinder is pi r squared h. And this one, r is a constant in this problem as well. But I'm going to say volume is equal to pi r squared h. And before I actually take the derivative of this, I'm going to put in, because I know radius is the same the entire time in the tank, regardless of what the water is. This would be 5 4 squared h. I don't know what's the deal with the radius being 4 and all these, but whatever. And again, we're not talking about the volume of the cylinder, like the container itself. We're talking about the volume changing in the water. So even though the container obviously will stay the same, is the radius staying the same in the water, which it is. The height is not. Okay, so I do this, and I'm still on non-calculus. Don't get sad, but this would be 16 pi h. Then if you take the derivative, wow, this is b1 dv dt. 16 pi is just a coefficient. And just like if I had 3h, the derivative of 3h would be 3, but dh dt. This is going to be 16 pi dh dt. Now I'm doing substitute all instantaneous rates and values of the variables. The only thing in this problem that I had was that dv dt is negative 3 feet cubed per second. I'm going to say negative 3. Actually, I don't even want the feet cubed. I'm just going to write negative 3. I'm writing this weird. Whatever. Negative 3 is equal to 16 pi dh dt. Divide on both sides. Be really careful about how you write this. This is okay right now. But if you say the height of the water is changing at a rate of negative 3 over 16 pi, and then you have to say the units. So in this one, we're talking about height. Height would be measured in the same thing the radius would be measured in, which is feet. Feet per, what is this one? Second, because we're talking about time in second, feet per second. And this would be, is there any particular moment, at any instant during the leak, so at any moment, because this is going to be a constant leak. So this is at any instant, there's no like time when the height is a certain thing, because there's no other variables in here to substitute for. Okay, so the height of the water is changing at a rate of negative 3 over 16 pi feet per second. If you put this as your answer, it would be marked wrong. Why? The reason is, it looks like negative 3 over 16 times pi. If you write yours like this with a little slash that way, you have to put parentheses, and then it's okay. It's even safer though to instead write it like this, to write negative 3 over 16 feet per second, and then you can save yourself from having to write in parentheses. Okay, that's all I'm going to do today because this is a lot. Stop, ask questions, ask me anything that you need to know. Thank you for following along with me. I appreciate you, and yeah, I just like teaching you, even if it's in totally weird ways these days. Okay, let me know if you need anything at all. Thanks. Bye.